Hello, Year 12s. I hope you're all keeping well. Okay, I'm going to create a video where I go through all of the examples from the Chapter 3 textbook, which is on sequences, the new topic that you're learning. So I hope that you find this recording helpful, okay, and I hope that it helps you complete the work that I've assigned. All right, so we're looking at sequences. So if you have a look at page 66 of the textbook of the new edition, it says that a sequence is a set of items belonging in a certain order according to some rule. So in 12 apps, we're going to look at number sequences, which is just when you have a pattern in a set of numbers. So if you have a look at example 1 here, you have all of these numbers. They belong to some pattern. Can you figure out what it is? So the pattern here is that to get the next number, you just take the current number, you double it, and then you add 1. Okay, so this works. If you double 5, you get 10. If you add 1, you get 11. If you double 11, you get 22. Add 1, 23, and so on and so forth. Okay, so all of these numbers belong to that particular sequence where to get the next term, you double the current term and you add 1. Okay, what you should know before we begin these examples is that each number in this sequence is a term. Okay, and so we say that the first term, number 5, is T1. We call it T1. It's the first term. So what you'll notice is that we actually write the letter T and then the number we put just below the T. Okay, so not next to it, just below, like a smaller number. 11 is term 2, so we'd write T2 equals 11. The third term, 23, is T3, T4, T5, and so on. Okay, that's just how we label the numbers in a sequence. All right, so let's get started. So let's start with the very first example. Oops. Question A. Determine T3. So T3, in our case, is just the third term. So 5 is the first, 11 is the second, 23 is the third. That's it. So T3 is going to be 23. Okay? 23. All right, let's look at the second one. Question B. It says, what's T5? Determine T5. So the fifth term in the sequence, 1, 2, 3, 4, 5, is 95. So T5 equals 95. Question C. It says determine T3 plus T5. So we need to add T3 and T5 together. So term 3, we already figured it out, it's 23, plus term 5 is 95. If we add those two terms together, we get 118. Let's do question D. We've got 3 lots of term 2. Okay, so 3 lots of term 2. So when you see something like this, it means 3 times term 2. So in our case, it's going to be 3 times term 2 is 11. So 3 times 11 is 33. Question E. 2 times T3. All right, so we've got 2 times, term 3 was 23, which is 46. Question F. Determine T8. Okay, so we need to figure out what term 8 is. So how many terms do we have at the moment? That's term 1, term 2, term 3, term 4, term 5, term 6, term 7. So we know what term 7 is, and if we continue the pattern, then we can figure out what term 8 is. Okay, so I told you previously that to get the next term in this particular sequence, you double the current term and you add 1. Okay, so term 8 is just going to be whatever term 7 was, doubled. So double term 7 and add 1. So in our case, it's going to be 2 times term 7 is 383 plus 1. If we put this into our calculator, we're going to get 767. Okay. All right, let's move on to example 2. Example 2. Generate the first 6 terms of a sequence for which the first term of the sequence is 73. So we know that T1 is 73, and each term is 5 less than the previous term. Okay, so we know already that T1 is equal to 73. To get what T2 is, because we need the first 6 terms, we're just going to subtract 5 from 73. So term 2 is going to be equal to 73, the previous term, minus 5, which is equal to 68. To find out what term 3 is, we take term 2, so the 68, and we minus 5 again, which is 63. Okay, so to get the next term, you take the previous term and you minus 5, because it says here each term is 5 less than the previous term. So to get term 4, we go 63 minus 5, which is 58. Term 5 is going to be equal to term 4 minus 5, so 58 minus 5, which is 53. And we need one more because we need the first 6. Term 6 is equal to 53 minus 5, which is equal to 48. Okay, so that's example 2. Now, you can have a go at exercise 3b. All right, before I continue, I am going to go through all of the examples, but pretty much to understand all the content for exercise 3b, you just need to understand these 2 examples, okay? Or actually just example 1. So have a go at exercise 3b, then when you're finished, come back to the video and then we'll go through the next examples, okay? All right, so hopefully you've done exercise 3b now. So let's go through example 3. All right, so example 3. A sequence is defined by T of n is equal to T n take 1 plus 3 with T1 equal to 5. Determine the first 5 terms of this sequence. So before we actually go into this example, there's a couple of things you should know, okay? Just some notation that you should be familiar with. So first of all, if you see T of n, all right, and I should write the n a little bit smaller actually, T of n, This generally just refers to the current term, okay? The term that you're on at the moment. All right, well, that's how I like to think of it anyway, the current term. And this can be anything. The n could be 5, so it could be term 5, or the n could be 8, term 8, it could be anything, all right? If you see t of n plus 1, this generally refers to the next term in the sequence. Okay, that's why there's the n plus 1. It's like what you were on before, but then just one higher. So if you're on t5 before, now you're on t6, for example. So the next term in the sequence. The next term. And if you see t of n minus 1, then this generally refers to the previous term. The previous term. Okay, so if we say Tn, the middle one is the current term, then T of n plus 1 is the next term, and then T of n take 1 is the previous term. All right, so keep that in mind. So if we have something like, let's say we have a number pattern, for example, e.g., say we have something simple like 3, 6, 9, 12. So the multiples of 3, 15, and so on. All right, so to get the next term, you take the previous term and you add 3. We could write this as what we call a recursive rule. All right, so a recursive rule is when you write down a rule or an equation to figure out the next term. Okay, so we could say that the next term, t of n plus 1, is equal to, the current term plus 3. Okay, so the next term is going to be equal to the current term plus 3. So we could write that as t of n plus 3. That's one way of writing this. And then we generally also put what the starting term is. So t1 equals 3. Right, that's one way of writing this. But sometimes you'll see it written differently. Okay? Sometimes they write it like this. T in terms of t of n. Okay? So the current term is equal to the previous term plus 3. You could write it like that. It means the same thing. The previous term, which is t of n take 1, plus 3, where t1 equals 3. This t1 is the starting term. So these two things, they mean the same thing. Okay? It just means to get the next term, you add 3 to the previous term. But they're often, but you will see sequences or recursive rules written in both ways. Okay, so the first way says the next term is equal to the current term plus 3. This one here says the current term is equal to the previous term plus 3. But it means the same thing. It just means to get to the next term, you're just going to add 3. That's what the rule is. All right, it's just expressed in a different form. Okay, so please keep that in mind. All right, so example 3. Let's do it. So example 3 now. I'm just going to keep this to the side. Determine the first 5 terms of this sequence. Okay, so we know that T1 is equal to 5. T2, so the second term, is equal to the previous term, add 3. Okay, so in here, it's expressed as the current term is equal to the previous term plus 3. okay? Which just means to get the next term, you add 3, all right? So this could have been written as t of n plus 1 is equal to tn plus 3. t1 equals 5. It's the same thing, okay? So this would be 8. This would be 11 if you add 3. Term 4 would be 14. Term 5 would be 17. And that's it, okay? Those are the first 5 terms of the sequence. That's all it is, all right? 5, 8, 11, 14, 17. Okay, so you really need to get used to this notation and how it's expressed. Okay, example 4. A sequence is defined by t of n plus 1 is equal to 2tn plus 3 with t1 equal to 6. Okay, so all this is saying is the next term, tn plus 1, is equal to 2 times the current term plus 3. Okay, so we already know that t1 is equal to 6. And we need to figure out the first 5 terms of the sequence, so 4 more. All right, term 2 is going to be equal to 2 times the current term plus 3. So 2 times the current term, which is 6, plus 3. So this is going to be 15. That's it, okay? The third term of the sequence, t3, is going to be equal to 2 times the current term which is 15, plus 3. Which is equal to 33. Okay, so term 4. Term 4 is equal to 2 times 33 plus 3. Okay, so if we do that, 2 times 33 plus 3, we get 69. And the last one, so term 5 is going to be equal to 2 times 69 plus 3, which is equal to 141. Okay, so here are the first 5 terms of this sequence. And each time we got the next term just by taking the current term, doubling it, adding 3. Okay, let's look at example 5. Example 5. A sequence is defined by t of n is equal to 0.5 multiplied by t of n take 1 with t1 equal to 400. So now this is expressed in a different way to example 4, okay? So technically it means the current term is equal to 0.5 times the previous term, okay? Which is just another way of saying that to get the next term, you multiply the current term by half. Okay, so again, this could have been written as t of n plus 1 is equal to 0.5 t of n, with t of 1 being 400. Okay, it means exactly the same thing. It's just written in a different form. Okay, so determine the first 5 terms of this sequence. So we know that term 1 is given to us, it's 400. To get term 2, we're just going to halve, okay, 400. So the current term is going to be equal to half of the previous term. So half times 400, which is equal to 200. That's it. Okay, term 3. To get term 3, we're just going to halve 200, which is equal to 100. To get term 4, we're going to halve 100. So we get 50. So just to get the next term, we take the previous term and we halve it. That's all it is. Okay. So term 5 is going to be equal to half of 50, which is equal to 25. Okay. All right. Let's move on to example 6. So for example 6, a sequence is defined, oops, too much. Okay, a sequence is defined by t of n plus 1 is equal to 4 lots of tn take 2 with t1 equal to 3. So this means to get the next term, you take the current term, multiply it by 4, then you take 2. So first term is given to us 3. So we've got 3, and we need to figure out the first 5 terms of the sequence, so 4 more. Alright, so the next term, term 2, is going to be equal to 4 times the current term, take 2. So it's going to be 4 times t1, which in our case is 3, take 2, which is equal to 10. Alright, to find term 3, we're going to go 4 times 10, take 2, which is equal to 38. To find term 4, not J4, that's term 4. That's equal to 4 times the previous term, which is 38, take 2. So this gets us 4 times 38, take 2, 150. And the last term that we need to find, T5, is equal to 4 times 150, take 2, which is equal to 598. Okay, so those are the first 5 terms of that sequence. Okay, let's move on to example 7. Okay, so example 7, a little bit trickier. Alright, so example 7 is here. Let's get straight into it. So, we already know that term 1 is equal to 5. For term 2, the next term, which in our case is term 2, that's the next term that we're figuring out, is equal to 2 to the power of the current term number. Okay, so the current term number, if this is the next term, then the current term number is actually 1, okay, n equals 1, multiplied by the current term. So this is the current term 5, all right? This is the current term number, this is the current term. So the next term, T2, is equal to 2 to the power of the current term number, 1, multiplied by T, the term n. So in our case, it's term 1. All right, so the n here and the n here have to align, which is in my case why I have a 1 here and a 1 here. All right, so it's 2 to the power of 1, which is 2, times term 1 is 5. So this is equal to 10. All right, let's do term 3 next. So we're saying that term 3 is the next term in the sequence. And so therefore the current term is term 2, which is 10. All right, so the next term is equal to 2 to the power of the current term number, which is 2, multiplied by the current term, T2. So this is equal to 4 times T2 is 10, which is equal to 40. Term 4 is going to be equal to 2, if we follow this pattern, 2 to the power of 3 times T3, which is equal to 8 times 40, which is equal to 320. And the last one, term 5, next term is going to be equal to 2 to the power of the current term number, 4, multiplied by the current term, which is T4. So this is going to be equal to 16 times 320, which is equal to 5,120. And I just realized that we only needed to do the first 4 terms, okay? So technically the answers are 5, 10, 40, 320, but I've just given you the 5th term as a freebie, okay? All right, example 8. Generate the first 6 terms of the sequence for which the 4th term of the sequence is 47 and each term is twice the previous term, add 1. Okay, so there's a couple of ways that you can do this. So one way that you could do this question is just by thinking of it intuitively. So Sadler actually goes through this in the book, in algebraically and intuitively. So if you say we created a table, so term 1, term 2, term 3, term 4, term 5, term 6, okay, we already know that the fourth term, T4, is 47, so we already know this value here. And it says in the question that each term is twice the previous term add 1. So each term, this is what they're saying, T of n is twice the previous term, 2 times the previous term, add 1, which means we can easily figure out what this is here, what term 5 is. If we just double 47 and then add 1, we get 95. Okay, so straight away we know that this is 95. Then we can also work out what term 6 is if we double 95 and add 1. So 95 times 2, take 1, 189. To figure out what, so we've done the ones in the future, okay? To figure out what the ones before term 4 is, well, just think about it logically, okay? To go from term 3 to term 4, you would have had to multiply term 3 by 2 and then add 1, okay? So if you were to go backwards, all you'd have to do, if you were to go backwards, is take 47, so grab 47, take away 1, and then divide by 2. So do the exact opposite. All right, so 47, take 1, divided by 2. 47, take 1, divided by 2. So that's going to get us 23. All right, and we can figure out term 2 in the same way. So we started with some number, then we doubled it, and we added 1. And the answer is 23. So to figure that out, again, just go 23 minus 1 and then divide that by 2. And see if this works. Is that true? If we doubled 11 and added 1, would we get 23? We would. Okay. All right, and term 1, we can figure out in the same way. 11 take 1 is 10, divided by 2 is 5. Okay, so that's how you do it intuitively. All right, so you could use an algebraic approach here if you really wanted to, if you really like algebra, to figure. So if you figured out term 4, 5, and 6, then you know that term 4, to figure out what term 3 is, you could set up an equation like this. You know that term 4 is equal to 2 times term 3 plus 1. Okay, so if we substitute the values in, 47 is equal to 2 times term 3, which you could even call x, plus 1. And then you just have to solve this simple equation. Okay, so if we took 1 from both sides, you'd get 46 is equal to 2 times term 3. And if we divided both sides by 2, you'd get 23 is equal to term 3. Okay, so you could set it out like this for the rest of it to find out what term 2 is and term 1, but it's probably easier just to think of this in a more logical way. All right, so let's move down to example 9. Okay, example 9. State T1, so term 1, and the recursive formula for the sequence 98, 91, 84, 77, 70, and so on. Okay, so first of all, term 1, that's easy. Okay, so we know that term 1 is just 98, so we can write that in straight away. Okay, term 1 is 98. So that part's done. And the recursive formula. Remember, the recursive formula is like an equation that will give you the next term, okay? So that'll give you the next term, and it has to be in one of two forms in this case, okay? So it has to either be t, something like t of n plus 1 is equal to t n blah blah blah, or it has to be t of n is equal to t of n take 1. Okay, so we looked at these forms earlier on. Okay, if you've forgotten, please scroll up. So, two ways of doing this, okay? First of all, you should notice that to get from one term to the next, you're just taking 7 away each time. So, you can write it like this. To get the next term, t of n plus 1, you take the current term and you take 7. Okay, so you grab the current term and you take 7. And you always have to give a starting point. So in our case, comma, t1 equals 98. That's one way of writing this. Or, so that's like this way here, okay? If you wanted to write it with the current term being the subject, you could write this like this. So you could say that the current term is equal to the previous term take 7. So the previous term, which would be t of n take 1, t of n take 1, and then minus 7. It means the same thing with t1 equals 98. So you need to be used to both forms. In a test, if it asks you write the recursive rule, you can choose which way you write it. Okay, example 10. Okay, let's go through example 10. So a sequence has a first term of 240, and each term after the first is equal to the previous term, increased by 10%. State T1 to T4 and the recursive formula for the sequence. Okay, so I want to start with the recursive formula first. So think about this. If you're increasing something by 10% from when you studied percentage increase and decrease, ultimately you're multiplying the amount by 110%. That's what you're actually doing, okay? You're multiplying by 110% to increase. If it was decreasing by 10%, you'd multiply by 90%. All right, so the next term in the sequence, t of n plus 1, is going to be equal to the current term multiplied by 110%, or in other words, multiplied by 1.1. Okay, so 1.1 times Tn. So this is what you do to increase something by 10%. You multiply it by 110%, or 1.1 as a decimal. Okay, so where the first term is equal to 240. So you could have written this again, or could have written it the other way. So you could have written this in the other form as the current term is equal to 1.1 times the previous term, so t of n minus 1, where t1 is equal to 240. Whichever way you prefer to write it, okay, is fine. All right, so that's the recursive formula. And then to state T1 to T4, let's do that. T1 is going to be equal to 240. They've already given us that. So 200, T1 is equal to T1 is equal to 240. Term 2 is going to be equal to 1.1 times term 1. So in our case, term 2 is going to be equal to 1.1 times 240, which is equal to 1.1 times 240 is equal to 264. So you can think of this as just finding 10% of 240, which is 24, and then adding 24 to 240. So if you did 240 plus 24, you'd get the same answer. Or you can use the formula, okay? Term 3. So if we're finding term 3, it's going to be 1.1 times 264, which is equal to 290.4. And then term 4 is going to be equal to 1.1 times 290.4, which is equal to 290.4 times 1.1 is 319.44. Okay, and the last example, which is example 11. Okay, so this example is going to involve a little bit of algebra, simultaneous equations, which you would have seen last year in 11 apps. So given that the sequence 3, 17, 73, and so on has a recursive formula that is of the form T of n plus 1 equals A times Tn plus B, determine A, B, and T6. Okay, so the best way to do this is algebraically. You could guess the numbers for A and B and see if it works for the rule, but doing it algebraically is probably the best way. Okay, so what you need to do is just pick 2 terms as examples. So you pick 17 and 73. Okay, so with these 2 terms, we know that 73, if we start off with, is term 3, okay? So we know that to get term 3, which is 17, we multiply A, whatever that is, by the previous term, okay, which would be T2, and then we add some value B. So if we substitute some numbers in here, so term 3, which is 73, is equal to A multiplied by term 2, which is 17, plus some number B. If we simplify this, we get 73 is equal to 17A plus B. So this is one equation that we've got. Okay, we could even label it equation 1. So remember with simultaneous equations, which is what we're going to use to solve this problem, you need at least 2 equations. If you've got 2 unknowns, so A and B, then you need 2 equations. If you had 3 unknowns, you'd need 3 equations and so on. So the second equation we can get from looking at 17, all right? So you know that 17, if we follow the same process, 17 is equal to a multiplied by the previous term, which would have been 3, plus some value b. So again, if we simplify here, we get 17 is equal to 3a plus b. So we've got two equations here. Let's call this one equation 2, equation 1 and equation 2, and we need to solve them. All right, so let's just put them together, one on top of the other. So let's have equation 1 here, 73 is equal to 17a plus b, and equation 2, 17 is equal to 3a plus b. All right, so when you're solving, that's equation 1, equation 2. When you're solving simultaneous equations, we want to find out what a and what b is. You've got two methods, substitution and elimination. Okay, so when you have two variables that can be easily cancelled out, in this case I've got a b here and a b here, that's when you'd use elimination. All right, so if I subtracted equation 2 from equation 1, the b's would cancel out. All right, and I know it has to be subtract, because if these two signs are the same, if that's whatever you're trying to cancel, if that's a positive and that's a positive, then I know I need to subtract. If they were different signs, like that was an add and that was a take, then I need to add them. Okay, so we're going to do equation 1, take equation 2. Or you could do it the other way, it would give you the same answer. So 1 take 2. All right, so let's see what we get. So if we subtract, if we do 73 take 17, okay, we get 73 take 17, 56 for the constant, 56. Okay, then we'll do 17a take 3a. All right, so every term in the equation has to be subtracted. So 17a take 3a is 14a. And if you did b take b, well, you'd be left with 0b or nothing, and they cancel. That's the whole point of doing this. So from here, we know that obviously a just has to be 56 divided by 14, which is 4. Okay, so you know that a is 4. And we can also work out what b is as well, just by substituting the value of a into one of our equations. So if we write out, say, the first equation, doesn't matter which equation you picked, 73 equals 17a plus b. If we just substitute this known value of a now, so 73 equals 17 times 4 plus b, and we figure this out, it would be 73 equals 68 plus b, which means that b would be equal to 5. So we know that a is equal to 4. We know that, let me highlight this. So a is equal to 4. B is equal to 5. So the equation is therefore, t of n plus 1 is equal to 4 times t of n plus 5. Oops. plus 5. Okay, where t1 is equal to 3. And you could test that this actually works, okay? Because if the first term is 3, if you multiply that by 4, you'd get 12, you added 5, you would get 17, which is the next term. All right, and finally, they wanted us to work out A, B, and also term 6. So if we just grab term 5, which is, so term 6 is going to be equal to term 5, which was 1,193, so 4 lots of 1,193, and then if we add 5 to that, we get 4 times 1,193 plus 5, we get 4,777. Okay, I hope that you found these examples and this video helpful. If you need any help whatsoever, please don't hesitate to contact me through the direct messages on Sector. Thank you.